Great. Thank you for having me here. So a few of you I remember seeing at the same talk last week. Nick warned me with this. But I don't know, the impression I got was today can be more leisurely and that I can give some more of the background that I kind of glossed over last week. But I also won't assume anything then. But okay, so it would be helpful if I didn't have that. Anyway, the the starting point of the talk is the dimer model. There's a few different ways of kind of trying to enter the discussion, actually. This is one of them, but maybe we'll consider other points of view later. So, and the dimer model is one of the most kind of central models in statistical mechanics. It's been studied since the early 20th century. A lot of the key work on it was done in the 60s and 70s by people like Castellane and Temperley Fisher. But then more recently, say in the last 20 or 30 years, a whole host of other connections to other parts of math, in particular geometry, algebraic and simplex geometry and representation theory, and also to other parts of theoretical physics have emerged. Connections which are kind of subtle and interesting in a lot of ways. I'll say some more about some of those as we go through the talk, but just to zoom out from a big picture point of view, one of the key things is the close interplay between graphs and their combinatorics. So the dimer model is a model about graphs, and algebraic curves, specifically algebraic curves in the algebraic torus. And there's kind of two sides of this relationship. One is that given a bipartite graph, so a graph defines this statistical mechanical model, you can form its partition function. And if you take the partition function of the dimer model on a graph in the real torus, that is naturally, that can be enhanced to be the defining equation for a curve in C star squared. So the partition function of a dimer model in a real torus gives you a curve in an algebraic torus. And then a kind of separate relation, though there are connections, is that if I have a curve in the algebraic torus, I can look at its projection to the real torus. So I take the arguments of each of its coordinates. That gives me a way of projecting from C star squared to T2 squared to T2. And in good cases, if you look at a curve, its coamoebae, its image under this coordinate-wise argument map, will retract onto a bipartite graph in a kind of visually reasonable looking way. And that has a number of implications for geometry related to that curve. So we'll talk about later. But okay, so here's a kind of big picture point of view. And you might just look at this, this little chart and think, okay, the number 2 is on both sides. Can I replace the number 2 with the number n for some bigger n? And there's a part of the literature that this talk is, in some sense, a response to, that explains how the dimer model generalizes kind of in the sense of this bottom arrow. So a number of authors, Futaki and Ueda in math, Franco, Lee Song, and others in physics, discuss generalized dimer models, and there's some kind of theory they developed, but it really just generalizes the bottom half of this picture. And so the goal of this project was to explain one kind of general story that puts this top arrow, which I'll call spectral data, into some kind of more general context that's kind of dimension independent. And this will be a story that in the kind of technical context of the story will be about constructible sheaves and mirror symmetry. Right. So there's the kind of big picture and the big goal. So let me recall some things about the dimer model and its solution. So we're going to fix a graph. As I said, kind of we'll be interested in a graph on T2. And I choose edge weightings for all of its, I choose a weight for each of its edges. In actual statistical mechanics, these would be real edge weights, and they would be roughly, they would correspond to some probabilities that a given edge would be in a perfect matching. A perfect matching is a subset of the edges such that every vertex is at the end of exactly one edge. And I'm going to assume that the graph is bipartite, so I can color its edges white and black such that any edge connects one black vertex to one white vertex. So anyway, the dimer model is the statistical mechanical model whose states are the perfect matchings on this graph. So the partition function of a statistical mechanical model is the weighted sum of its states. So here, one is interested in computing the weighted sum over the perfect matchings in a graph. And for a finite graph, that problem was solved by Castellane and Temperley Fisher in the 60s. It can be expressed as a certain determinant. And I will show you this Castellane solution here in this little example. So here we take this fundamental domain for the square lattice. So there's 8 edges in this graph. I pick 8, I give each of them a weight. If there were, well, I guess I'll continue and then comment on signs. So step 1 to write down the partition function is to write down a certain matrix. The matrix has rows corresponding to I'm going to make some convention choice later. I guess the rows are the white vertices and the columns are the black vertices. Obviously, that's just a convention. And then each entry is so an entry corresponds to a pair of a white vertex and a black vertex. So this top left end, the first row corresponds to that white vertex. The first column corresponds to that black vertex. And this top left entry is the sum over the edges between them, weighted by their edge weights and also by a monomial in 2 variables, x and y. And I use that monomial to count when edges cross the boundary of this picture. So this is a matrix valued Laurent polynomial that we'll call the Castellane matrix of the graph. And the determinant of the matrix, which is down here, up to some signs, gives the partition function for the dimer model. So for example, a perfect matching on this graph would consist of, one example would be that horizontal edge and that horizontal edge. The weight is A1 and B1, which is that first term there. If we'd worried about, so one of the things that Castellane figured out was how to sprinkle in signs in a way that cancels out all the minuses in the determinant. For what we'll be discussing, I don't really care about those signs, so I'm just going to not worry about them. And I'm going to allow my edge weights may as well be complex as well for the kind of geometry. Good. So the x and y's, I have this edge that doesn't cross the boundary of my fundamental domain. This edge does. So I label that with an x. And there's a convention here where, say, this edge labeled B2, it also crosses that the vertical edge, but it does so with a different orientation. So I remember that with an x inverse, there's some convention that says exactly.
So what does this matrix well define?
The matrix depends on the graph and it depends on the choice of fundamental domain. What's not going to matter is, so if I change,
like even for the determinant, is actually an intrinsic quantity that's an intrinsic object that's associated to the model?
No, a priori, the matrix is just a mechanism for producing the partition function.
The partition function is number based.
Yeah, or it's the number, the partition function, it's the weighted sum of the perfect matchings. So the point is that every term in this determinant corresponds to a perfect matching on the graph. So for example, C1 times D2, if I look at the edge labeled C1 and the edge labeled D2, those form a perfect matching because every vertex is at the end of one or the other of those. So right now there's, yeah, okay. Right now there's no meaning to those. So those are just some extra variables that have been put in here for mysterious reasons. Uh, and indeed, okay, so the point is that once you include those variables, of course, the kind of raw partition function, really you should say, well, you just plug in one for those variables. When I put them in, now this partition function gets enhanced to the equation of a curve in C star squared. Now this is an equation in two variables. The vanishing of that equation is called the spectral curve of the model. And it's in significance, it's not a priori obvious, but it was realized in this work of Kenyon and Kunkov and Sheffield, their annals paper on dimer models and amoeba, which is that, so in addition to this finite graph here, I can unroll my graph on the torus to an infinite graph in the plane. I can ask questions about the dimer model on that. That becomes much more subtle, and there's new kind of interesting asymptotic questions. But they showed that basically the solutions to many such questions about that planar dimer model can be reduced to questions about this spectral curve that we extract from the graph on the torus in this way. And in particular, the amoeba of that spectral curve controls, in some sense, what kind of random perfect matchings look like in the plane. So it's not obvious why you should put those variables in there, but it turns out to be important through the study.
Sure. Can I ask a question?
Mhm.
What's the relationship between the spaceship so far this week, the finite curve and like more neutral product geometry, are equal to pi?
Uh,
Whatever.
yeah, so that's a great question, actually. So the Newton polygon of this matrix turns out to be very important. Let me say, okay, let me say one more thing and then I'll try to say some more. So a feature of this relationship, so from a dimer model, you get a spectral curve. You get that curve together with some additional data, a line bundle. Maybe to say two different versions of that. First, wherever the determinant of this matrix becomes zero, then then K stops being invertible at that. I think about values of X and Y. And so at any point where the determinant vanishes, I have the co-kernel of K, and that is generically will be a one-dimensional co-kernel. And so I have a line bundle on the vanishing of det K given by the co-kernel of K at that point. Or to say that more globally, I could think of K itself as not as a family of matrices. I mean, I can think of it as a homomorphism of free modules over the Laurent polynomial ring. And when I take its co-kernel as a map of free modules, that is some other module, which now that's the data of a coherent sheaf on the torus, and that will be some sheaf which is supported on this spectral curve. Okay, so any curve, it turns out, arises in this way for some bipartite graph. To say one, you could read, and I'll tell you how to read off. Before I explain that comment, I mean, there's a. So I'll show you how to read off the Newton polygon of the curve without computing the matrix. So if I take all the I'm going to draw a picture on this graph where I turn, let's see. Imagine I'm going along the edges. I turn right every time I hit a white vertex. I turn left at black vertices. Right, left. And I get a path like that. And now I look at the homology class of the path that I just drew. And it's 1, 1. And now I keep going. So let me try to keep connecting here. Left at black, white at right, left, white. So there's another curve that class is 1, -1. And then if I keep going here, I will arrive at this picture, which you will notice is the Newton polygon of that equation in the bottom left here, up to a translation. So there's a constant term, there's an x term, there's a y term, an x inverse, and a y inverse. So you can convince yourself. So to convince yourself that every curve arises as a spectral curve, you have to check, first of all, this prescription that I just wrote down indeed is the Newton polygon of the curve. And now you have the combinatorial question of, given, you hand me a lattice polygon like this, I draw some arcs that represent those homology classes. Can you rearrange them so that they came from a graph via this construction? And now that's a combinatorial question that you can kind of analyze directly. So anyway, every curve is of this way, and all right. So this spectral data was studied in further work of Kenyans with Goncharov, and they studied how these spectral maps relate when you change the graph. So first comment is that, so this construction depended on an edge weighting, but if I think of my edge weighting as specifying a connection on the graph, where say I put a one-dimensional space at every vertex, and then read these as parallel transports from black to white, the resulting spectral data up to isomorphism only depends on that edge weights up to gauge transformation. So I can really think of this as a function from the space of rank 1 local systems on the graph, which is an algebraic torus of some dimension, and B1. I have a function from that torus of local systems to the space of curves with line bundles on the algebraic torus. And what they showed is that when you vary the graph in kind of standard local ways, so there's a move, if you have a square face of your graph, as we do here, I modify the picture by inserting a smaller square there. So that's a certain operation on graphs. And then you also allow yourself the operation of kind of removing bivalent vertices. So if you consider graphs up to those two operations, the resulting maps give what's called a cluster atlas on this moduli space. So first of all, this gives you an open piece of this space with curves with bundles. So if you fix the Newton polygon of your curve then not just a generic curve, but a generic curve with bundle will be in the image of one of these maps. And they so you have many different maps on the same component of this moduli space, and the transition functions between those open sets are of a specific form. So seeing the form itself is not that enlightening, but just to kind of write it out. So if I call this, let me call x1 imagine this is part of a bigger picture for a minute. Right, so locally near a square face of the graph, I have coordinates on the space of local systems given by the polynomials around each of the faces. So that's some natural coordinate system that I could put on the space of local systems on this graph. And then if you unwind it, the rules here for how these change under this change of coordinates is that the middle one is inverted and these surrounding ones get divided by 1 plus that middle holonomy, or its inverse.
There's some sense that this moduli space is the thing you're really interested in.
Absolutely.
Things and the combinatorics of the graph, the way of getting at that.
I would say that's exactly correct. Well, okay. So kind of part of the point of view here is to change the focus to be that moduli space. And then you think of these, the construction as being charts on that moduli space. And in some sense, the goal of the talk will be to get closer and closer to just looking at things from the point of view of that moduli space. But okay, so they explained how these different graphs, what are the coordinate changes between the different charts here, and they have some standard form, which let's see.
Thinking about this. With faithful for separation, but as on purposes to generalization.
Which operation? Mm-hmm. I don't think it's renormalization, but it's basically saying that if you do a gauge transform, so like in this graph, I would have one edge weight, and here's a graph where I have two edge weights. But if sorry, I actually should have. Yeah, it's more you're shrinking that. Basically, what this amounts to is the statement that if you A1 and A2 don't contribute they will get normalized away once you compute A. Why did maybe okay, here's a corrected version of my picture. I don't know if that addresses your question more. But the statement is if you remove this vertex, you don't change the spectral data. That's part of the statement. All right. So part of the background for the talk is the theory of Coulomb branches. Let me give a little bit of context for that. So if you have there's some notion in physics that when you have a suitable supersymmetric QFT in different dimensions, you get various geometric objects out of it. And one of them is the so-called Coulomb branch. It has been a big of interest from a range of mathematical perspectives to recognize different mathematical objects as Coulomb branches of different theories. So some key examples are spaces of, so the Hitchin moduli space of some curve. So that is, you have a Riemann surface and you choose some data of, say, a compact group, maybe some additional decorations on your surface. You have the moduli space of solutions to the Hitchin equations, which is, depending on the complex structure you look at, the space of Higgs bundles or the space of flat connections on that surface. These can be recognized as Coulomb branches of certain theories. And here's okay. So there's one class of examples. Braverman, Finkelberg, and Nakajima described another class of examples given by taking homology for K-theory of so the homology of the affine Grassmannian, or they defined a family of spaces that live over the affine Grassmannian associated to the choice of a representation N of G. And many interesting things come out of this construction. Got Dahas in here, spherical Dahas, different kinds of Lie theoretic varieties, open Richardsons, and affine type can be realized this way. And in principle, these moduli spaces, so expect say relative Jacobian of those. Say curves and torque surfaces. So it's expected that these moduli spaces are Coulomb branches of certain 5D theories. In this BFN world, taking the homology of Burgi gives you an example of a Coulomb branch of a 3D theory, and then taking the K theory of one of those spaces, or taking a Hitchin moduli space, those are Coulomb branches of 4D theories. And there's a kind of expectation that some of the time, you should also be able to take the elliptic homology of one of these spaces, and that should give you a prescription for the Coulomb branch of a 5D gauge theory. And it is a kind of open question to actually carry this out and show that you get one of these moduli spaces. So in principle, this construction that we're kind of discussing here connects to elliptic homology of BFN spaces, which is one of the kind of interesting things in the background, but that's kind of we're a ways away from being able to make that precise. But in the background, the context is here's this world of Coulomb branches, here's a class of them, and this is substructure. Yeah.
Is there a precise conjecture one could make about like, well, here's a particular thing, it's curves and it's C star squared along the hill, given by the elliptic version of the VFM construction for some input?
That's so up to a point. So what will be true is that I think they will be like overlapping, but not contained in the other. So I don't think every space of this form you would expect to come from a Lagrangian theory. So some of them will. So there's a kind of subtle question. So yes, and here the toric surface is C star squared. You could naturally there's a natural partial compactification. The spectral curves that you get for a fixed graph will have, they'll have a prescribed Newton polygon, and that will make it. So there's a kind of natural minimal compactification that they bend to. So you can. You can consider them in that toric surface if you want.
Right. Well,
I don't think so. Well, there's some kind of standard packaging of homology K theory and elliptic homology as a kind of rational trigonometric elliptic or 3D, 4D, 5D, or 4D, 5D, 6D trichotomy. Yeah, this is some version of that would be the natural way of extending that trichotomy here. Right, okay, so the context for this statement that okay, you have these moduli, this moduli space with curves and bundles, the spectral data construction gives you a cluster atlas on that is these spaces in particular fit into this larger theory of Coulomb branches, and there's other expectations for kind of why and where. So for example, the Hitchin moduli space has in its Betty complex structure has cluster atlas due to Falk and Goncharov. And some of my work with Caddis, we extracted cluster structures on these K-theoretic Coulomb branches by looking at T structures on coherent sheaves on these spaces. And here's some way of accessing something about cluster structures on these 5D Coulomb branches, which conjecturally should hook up to some story about BFN spaces. Right. So that's questions about this kind of background so far. Right. Okay. So one thing that actually, so this this line of I don't know, inquiry here actually grew out of some old work that I had done trying to understand better these Betty moduli spaces and their cluster structures. So there's there's a general construction that takes a bipartite graph on a surface and produces a Lagrangian submanifold of the cotangent bundle to that surface. So this was an idea that kind of came out of this Goncharov-Kenyon work, and then we worked out with Truman, Zaslow, and Shende. And then we showed with Truman and Zaslow that this gives you a mirror symmetry interpretation of this spectral construction appearing in the dimer model. So if you think of it formally on the previous slide, the result of the construction of the curve and the line bundle was a map from local systems on the graph to coherent sheaves on the algebraic torus. If I have a Lagrangian in the cotangent bundle of T2, so T star T2 is the mirror symplectic manifold to C star squared, the complex manifold. So mirror symmetry tells you that the wrapped Fukaya category of T star T2 is equivalent to coherent sheaves on C star squared. The Fukaya category has as its fundamental object Lagrangian branes, so a pair of a Lagrangian together with a local system on it. And if you are graph, so here the claim is that there exists a surface L gamma, which first of all, it's a ribbon thickening of gamma. So they have the same, they're homotopic. So in particular, local systems on L gamma are the same as local systems on gamma. And if you have a fixed Lagrangian, then local systems on that parameterize a family of objects in the Fukaya category, hence a family of objects in the mirror. So mirror symmetry so the fact that the L gamma retracts onto the graph tells you that local systems on the L gamma are the same as local systems on gamma. But then mirror symmetry tells you that, well, local systems on the L gamma parameterizes some family of objects in coherent sheaves. And so our claim was that for this choice of Lagrangian, that mirror map is exactly this spectral data construction. I want to say that a little more formally. So I have to either tell you something about how the Fukaya category works, or I can do something different. It's just tell you something about how constructible sheaves work. So I can realize the notion of mirror map, which I just kind of said in referencing the Fukaya category and implicitly Floer theory, but actually that statement is something that I can make precisely entirely as a discussion about constructible sheaves. So let me explain a bit about how that works. So there's kind of two basic principles. The first is that I can go from Lagrangians in the cotangent bundle of a manifold, maybe decorated with some local system, to sheaves on the base of that manifold. So there's a claim, there's different versions of this principle kind of that appear in different ways in the literature. The version that I have in mind most precisely is a formulation of Jin and Truman, and particularly showed if you have an exact Lagrangian with some constraints on its asymptotics, then you get a fully faithful functor from local systems on that exact Lagrangian to sheaves on the base manifold. I call M if L is in T star M. And we call that the sheaf quantization of the pair L and E, where E is the local system. So this is a kind of variation on other ideas of Nadler and Zaslow and Guillermo Cachoeira and Shapira. But anyway, so this is one basic building block. I guess I should say, so this is a kind of inverse to the notion of this singular support of a constructible sheaf. So maybe let me say just a couple words about singular support. I'll at least say an example here. So if you have if you have a sheaf on a manifold, let's say it's this, in hindsight, it'll be constructible. So we have so there's a prescription due to Cashwar and Shapira of the singular support of F. This is going to be a subset of the cotangent bundle. And the idea is that the subset of the base, where does this intersect the zero section? It's exactly in the support of F. And then the non-zero covectors contained in the singular support tells you, kind of measure how far is F from being locally free. So if you have a locally free sheaf, a local system, then this will just be the locally constant, yes. Then this will just be the zero section. And in the so I'll say this measures the failure to be locally constant. And let's see, so if I have the skyscraper at a point X, then I get the cotangent fiber at that point. Or in a picture, take M equals R, there's X, and there's that Lagrangian. And let's say if I did the constant sheaf on some interval, then I would have that interval and then half of the codirections at one point or the other. And if I flipped the boundary conditions, I would flip the direction that those intervals go. All right, so there's a few examples of singular support. And then the idea of this quantization would be that, in particular, if you started with the Lagrangian that looked like a smoothing of this singular support, you would recover the original sheaf here. So for example, if we took L to be something like that, then Q of L, so L is contractible, so there's no, just take the constant sheaf. Your quantization would get you back the sheaf whose singular support L had smoothed, right? So this sheaf quantization is roughly some kind of inverse to the formation of singular support. And now if the claim, if I have a constructible sheaf on Tn, there's just a good notion of the mirror coherent sheaf. Point one is that coherent sheaves on C star to the n are tautologically the same things as local systems on T to the n, because a local system is the same as a representation of the fundamental group, hence of the group ring of the fundamental group. So pi1 of Tn is Zn, and the group algebra of that is just the Laurent polynomial ring, so functions on the torus. And there's a canonical way of taking a sheaf and turning it into a local system, because the inclusion of locally constant sheaves into all sheaves has an adjoint, or it has both adjoints, but I'm going to take its left adjoint. I'm going to call that W for wrapping. And I define the mirror of a sheaf on Tn to be its image under that wrapping functor W. Why is that a good name? Let me tell you about. Okay, so, I guess I forgot to say something very important on the first slide, which is that my co-author Chris Kuo, who's now at Bonn, he studied these wrapping functors in his thesis, and in particular, he showed that some version of the following statement, that W of F is a colimit of F under positive isotopies of the cosphere bundle of M. So there's let me draw in a cartoon what this says for an example like this. So I can notice that the pictures that I drew down here, they look like this picture I drew up here, where I started pulling those these two apart. And as I do that, I get a system of sheaves if I pull it in one direction here. As I open up this interval, I get maps between the resulting sheaves. And so I can look at the so when I look at W of C of X, this is the same as the colimit of I take an open interval around X. All right. So imagine this picture here, but these are being pushed further and further out. And eventually in the limit, they disappear completely. We would say they've been wrapped away. So I'm kind of grabbing things at infinity in the cotangent directions and taking them off to infinity. And the claim is that that is the kind of geometric description that this left adjoint W admits.
So this is really just R. Like if your manifold is S1, which local it look the same.
Good. So then there would be real wrapping, yeah. So the next level here is that, yeah. So there maybe. So W of, so now let me do pi will be the projection from R to S1.
So I guess in general, it would be the same kind of thing if you know.
Yeah. So this will still be the same. But I mean, this will be compatible with this push forward. All right. But now what's happening is on the S1, so here as I take this and I stretch it out, kind of nothing's changing in the middle of the picture. But on the S1, as I stretch it out, eventually it starts to cover itself. And so what that means is that the stalk at a point, I get lots of copies picked up. One copy for each element of the fundamental group. So in particular, here's we would just get the structure sheaf of C star. And so in particular, this is if you're kind of, enough of an example has been written down to see how this is consistent with normal expectations for toric mirror symmetry, where you would want the mirror of the structure sheaf on the coherent side to be given exactly by a cotangent fiber. In other terms, that it's a section of the SYZ fibration, and indeed that matching is implemented by what's described on this slide, even though we haven't, touched any FLIR theory at all. Okay, so there's mirror interpretation of the spectral map. Okay, so now here's a next, I guess yeah, okay. So there was the picture of, so this L gamma, so more precisely, the kind of gray shaded part of the picture is the image of L gamma downstairs. And just like here, the quantization of a Lagrangian is supported on its image under the projection of the zero section. So the sheaf you get out from this construction will be supported on a bunch of regions around the vertices, and it'll be alternating in degree 0 and degree -1, one-dimensional pieces. All right, so now you can ask, what happens when I take this picture and I try to contract everything onto the graph? So there's a well-defined notion of the limit of a family of sheaves. So first of all, I can carry out this quantization in a family. So the point is that when I look at the family of sheaves that let everything contract onto the graph, and if I have, so that's a sheaf that's parameter. I get a sheaf for every positive number. If you like, let t be some variable controlling how close things get to the graph. And so let's say, so I have a sheaf on Tn times this open interval. I can push that forward to Tn times the closed interval, starting at 0. And then I can restrict, or maybe I'll write, I can restrict to just what's happening at 0 here. So this is a good notion of the limit or the nearby cycles of a family of sheaves parameterized by the positive numbers. And you can compute this here. So, and here's the claim is that the resulting limit, which I'll write as E prime, is related to our edge weights by taking reflection functors. So if I think of my original edge weights as being parallel transports, like they are over there, I can look at the following local move where I replace, so here I have a white vertex going out to some number of black vertices. Call them A, B, and C. Or sorry, it's receiving arrows from all of those. I can look at the kernel from the sum of those spaces. This was CW. Let me call this call this VW. So that's some new space I could cook up out of this data. It comes with projections back onto CC, CA, and CB. So this kernel fits into a representation of the quiver that I got by reversing all the arrows at that vertex. This operation is called the reflection and a sync vertex. And now the statement is, okay, do this at each of the white vertices in the right picture. You get some representation now of this reversed quiver, which now I want to take this and think about this as a constructible sheaf on the graph. And the claim is that that is the limit of this family. So here I'm thinking I have a constructible sheaf where I have a three-dimensional stalk at each of these white vertices. That 3 is coming from there's 4 adjacent vertices, 4 minus 1 is 3. And then I interpret these maps as the nearby stalks are all one-dimensional, and now that is the exit map as you walk away from the white vertex to the generic stratum. All right, so there's an answer for what this limit is, and taking this limit commutes with W, which isn't totally free, but it's not that hard to show. Okay, so the upshot of all this is that that spectral map that we'd seen on the first slide, I can reformulate as follows. First, I replace our local system with this other kind of reflected constructible sheath E prime. And then that sheath is just a mirror to the spectral data. I get the spectral data from there by just taking the mirror of E prime. So I can repackage the whole discussion as you have a pair of a mirror pair of a constructible sheath and a coherent sheath. And the graph and the spectral curve are just what you get by taking supports on either side of that mirror pair. Right? And now the kind of claim of the talk is that refactoring things this way is exactly the thing that you need to do to see this as part of a general discussion about tori of arbitrary dimensions, which was the kind of initial agenda for the talk. So the claim is that now we started with this spectral data discussion in the dimer model. We've kind of adapted our point of view a little bit to reframe it in terms of a constructible sheath supported on the graph and its mirror. And now the claim is that that is something that we can generalize. Questions before I change slides again? Yeah.
I'm supposed to think of this epsilon prime. So like you started with this epsilon and expect this epsilon prime by sort of taking this kernel procedure. Right? But how should I think of it as like objects?
So as an object, you just think of it combinatorially. I'm saying that, okay, so what's a constructible sheaf is something that assigns to each, you have some stratification. To each stratum, you have a local system, or if the strata are contractible, just a vector space. And now I haven't told you all of the vector spaces for the strata, but I'm saying that the vector space at the white zero-dimensional strata are C3s. The ones at the black ones are just line C. And then on the edges, they're also C's, and the map that relates the black vertex to a generic stalk on the edge nearby is the identity. So I have this sheath is 0 in the, if you like, in the two-dimensional strata in the faces. It's rank 1 on the one-dimensional strata, and then it's rank 1 or 3 at the zero-dimensional strata, depending on their color. And then more generally, at a white vertex, it would be like the dimension would be the number of surrounding edges minus 1. Yeah.
They are near dual.
They are Uh, it's like partially Verdier dual. The point is, this is it's like this is the Verdier dual to the local picture there. Yeah. So you're like taking a Verdier dual at the white vertices, if you like. Yeah, indeed.
Also, a organizational question.
Yeah,
To take a break.
this is a good break time around now.
That's
Yeah, that sounds good. I turn this off. If you have a there's too much like study. I have a higher genus of this. And imagine I have some triangulation of it. If you can replace this triangulation with a graph, where the local feature is vertex in the middle of each triangle. So I can associate it to a triangulated surface, a graph like this. And now if you can play this construction, and the interesting thing to do is to really there's not like another secret marker box in here.
There's a blue one over there. Does that no more?
Yeah, that's the one.
So that's the one I exiled.
Oh, okay.
That's really good.
Yeah, sorry.
That's okay. Anyway, if you unwind this whole construction, you can do something rather than taking the blue strands and pulling them in towards the graph. You can try to pull them as far away. So here, like you would have some strands passing near this white vertex. Try to pull everything away to surround the black vertices, which are to be thought of as punctures on the surface. And you wind up realizing that you kind of get little spirals around the punctures. And you can still build a family of sheaves. And now at the end of this family of sheaves, so now your surface kind of looks like there's some punctures which have little spirals around them. And the output will be a constructible sheaf on the surface, which looks like it will have some generic, it will be kind of generically ranked 2. And then kind of in between these two arcs will look as rank 1, and then it'll be 0, kind of right next to the puncture. And so this now looks like, okay, you have the data of just a local system on the punctured surface, together with some kind of filtration data around the punctures. And so what you get out of this kind of higher genus surface with the triangulation, you can still play this game about turning this triangulation into a bipartite graph. You'll link some Lagrangian, get a family of sheaves. That family of sheaves will now parameterize an open subset of this. Now consider, so the analog of the space of curved line bundles is this decorated character variety in this punctured surface, decorated in the sense of a rank 2 local system, but then also some filtration data for punctures. So there exists a kind of this like bipartite graph to Lagrangian correspondence. One of the things it does is give you a kind of uniform symplectic perspective on a number of examples which are kind of different in flavor in what's the moduli space, but you can still kind of relate them to the same underlying symplectic.
Is that this from exhausting?
Yeah, or so the paper with Vivek too, where we first started this up. We were kind of more focused on these samples. and the respondent, and then the paper. So there were two self-references on the slide.
Yeah,
So there were the first four author paper where we kind of introduced this geometry, and then looked at some of these Venn spaces. And then the follow-up paper, which is driven as well. We looked at these examples to include our.
sorry, I think I was asking a different question, because there's this work just from.
Oh,
And then some follow-up where they kind of study some bipartite graphs and services, is that?
yes, it's related. Yes.
For instance, I mean, explain some follow-up work to that.
Yeah, there's a few things to say there. So they studied, you have maybe I should say it's related.
Okay, yeah.
Okay, okay, so the thing that I was about to start explaining with this, so this is the claim that, okay, now we've kind of reformatted our perspective on spectral map as a mirror map, and claim this new perspective makes it clear that there's a general picture behind what's going on. So here's the general picture. So one way of saying what the key point is that, so we had this moduli space that curves with bundles, and we had these open subsets that were labeled by different bipartite graphs. The bipartite graph gave you the spectral data via this Castellani matrix, via presentation by this matrix. So from the point of view of the spectral data, that's a certain free resolution. And fixing the graph and letting the edge weights vary corresponded to fixing what are the exponents in that free resolution and letting the coefficients vary. So we can try to do that more generally, or we can ask that same question now for any free resolution.
Sure, by coefficients, you mean the differentials?
In the difference, yeah. So yeah, I think about K is the, yeah. K was the differential in a resolution. So I'm going to try to just kind of invert the process that would write down the matrix from the graph. So I'm going to try to write down the graph from the matrix and actually see that it wasn't so important, it was just a matrix, it could have been any resolution. So here's how this will go. So the starting point is for the construction is a free resolution. I capitalize a basis for it. And the key data is what are all the exponents that appear in the different entries. So I'm just going to write EJI. This is one of the slides. You're not really meant to read this slide. But so there will be some examples in a minute. But the idea, the structure of the definition is going to be, we pick a free resolution together with a basis. The basis is indexed by some set called that capital I. I'm going to define for each basis element a subset of Euclidean space Si. That's the goal of this slide. How do I build these subsets Si? They're all going to be things that were tracked to some particular point. So I'm going to pick a collection of points first. I'll pick an Xi for each little I, a bunch of points in Rn. And now I build these SIs by descending induction of degree. So basically, if little I, so capital I is indexing elements of this resolution, a basis of the resolution. So every basis element has some degree. So you're going to start at degree 0 by just taking the SI to these points. And then in lower degrees, the definition says something like take your points and attach cones to translates of the subsets you've already built. That's the flavor of the the definition. We'll walk through it in an example. And this is the kind of minimal way of guaranteeing two things. First of all, each of these subsets is contractible. It can be a union of a bunch of cones at a common point. And I'm arranging that whenever I have a coefficient of c to the m in some differential going from the matrix element that goes to the ji matrix element, when that has a certain exponent m, I have some containments among the translates of si and sj. The m is in the ji actually. And because of this containment, if sj plus m is contained in si, well, I have a restriction now from the constant sheet on the bigger thing to the constant sheet on the smaller thing. And then I can push that forward to the torus. And then after pushing forward to the torus, that integral translation doesn't matter. This projecting bit torus is just modding out by integer translations. And so I can take those sets, I can now sum together the push forwards of their constant sheaves, and I will be able to build a certain complex of constructible sheaves on Tn now. And claim is that, okay, this sheaf or complex of sheaves is mirror to the module that we start off. So we pick the free resolution of some m. And now we've built a constructible sheaf which is mirrored to that. That's claim, and the claim is that it is one of these reflected local systems in the case that we started with, and you just have a two options, even with some more dimensions. And then we call this a tropical Lagrangian coamoebae. So the support of this sheet brings to you that, which just some context for motivating the terminology. I mean, so there's there's the notion of a tropical variety, which is some special subsets of Euclidean space. Here's a tropical curve from a central example. And one way of saying what is a tropical variety from the plane of symplectic geometry is that there is a Lagrangian that it's like a generation of amoebas of Lagrangians. So I can find that here's an R2, but then C star squared, like the log. So I take the amoeba projection by take on logs of the norms of the two elements, rather than the coamoebae, we mostly even looking at, here you take the arguments. So there's a family of Lagrangians whose amoebas so that I can write a tropical variety, at least that are many tropical varieties. I can write as you have a family of Lagrangians such that their amoebas are degenerating. The limit of their amoebas is this tropical variety. So the point of this picture is directly analogous to the picture that we were analyzing a minute ago, where we had this L gamma, and I looked at some degeneration where its coamoebae was kind of retracting onto something that was a minimal. So that's because that picture is kind of a coamoebae version of this picture, that's called a tropical Lagrangian coamoebae. And the idea of the construction, like how you invent that formula from the previous slide. So a given module M or a given coherent sheet F will generally have many different mirrors. Okay, there's a lot of degrees of freedom. For example, I could take
I could just think of that sheaf, regard it as a locally free sheaf on the torus. So that was, just consider the local system directly corresponding to M. And that thing has a maximal coamoeba, right? So there's many mirrors. Typically, their coamoeba are very big, but the problem becomes constrained when you try to make their coamoeba as small as possible. So for this, these spectral data sheets, curved with line bundles, we found that we could find a mirror constructible sheet supported on a graph. But there's no way I could have kind of degenerated to get a mirror that was supported on something zero-dimensional. The zero-dimensional things are skyscraper sheets, and as we already said, their mirrors aren't free, are just going to be copies of the structure sheet. So the minimal dimension of the support of the mirror of M is some kind of interesting constraint on M. And the precise conjecture is that it's the same as the projected dimension of M. So conjecture, if you have, so I fixed the module M for Lagrangian polynomial ring. If I have a constructible sheaf which is mirror to it, then the support of that sheaf has to be at least the projected dimension of it. So we can prove this if I further assume the depth is concentrated in single degree itself. But that's the kind of heuristic picture here. And so the idea of the construction is it's trying to produce something that saturates this bound. Right. And then as we said, you can kind of now make sense of what are the generalizations of these contra Kenyan cluster charts now for other parts of the moduli space of G's. The point is they're fixing the discrete data in a pre-resolution and letting coefficients spare. Okay. So here's our example revisited just to illustrate that indeed the prescription that I just laid out inverts our original construction. So now we start with this matrix thought of as the differential in a resolution. I'm going to number the sum ends. So R2 is Lagrangian polynomials in two variables now. Now, if I number the sum ends from left to right, our definition said, okay, build up some subsets of the plane. Here's the plane. We need to build S1 through S4. The sets, and I should pick a point for every sum n, so I'll pick x1, x2, x3, and x4. The definition said the sum ends in degree 0. You start by defining the s's for those sum ends, and you just take them to be those points. S3 and S4 are x1 and x4. And then to S, these sets were something you build by looking at the exponents in that matrix. And so specifically, if you unwound what we were looking at, would say to build S1, take X1 and connect it to some translates of S3 and S4, which are just points, by the entries in the first column. So in that matrix there, it's kind of like column 1, column 2, row 3, row 4. So column 1, row 3, and see A1 plus A2X. So I connect X1 to X3 just by itself, and then X3 plus the exponent of X. I think of as the vector 1, 0. So there's X3. There's X3 plus 1, 0. That connects those to X1. Likewise, in the column 1, row 4, I see the exponent 0. So I take X4 plus 0. And then I take X4 plus 0, 1. And so, yeah, so that's S1. S2 is this plus sign thing. And when I look at the image of those, I get back the graph that we started with. And when I take the a sheath. But then on the previous slide, I said, look at this complex here. And what does this complex look like? So this part is just, those are skyscraper sheets at the points, X3 and X4, so they're skyscrapers at the whites. And then this is the sum of the constant sheets on the two plus signs. So that's something that's generically one-dimensional on the graph, but then it has a degree 4 stop at the white vertex. Because I constant sheet on S1, C could be a one-dimensional space there and there, and then the one in S2. So you get at the interesting vertex, you have dimension 4 goes to dimension 1. The kernel has dimension 3. This is that sheet that we've seen from before. So we indeed get back there in this graph case, we get back the sheets that we're supposed to. But in this uniform way now you can input any other resolution. And here's a picture of what you get out when you input a resolution, the Kuzel resolution for a curve C star cubed. And so without going through the details here, now you're going to get out a two-dimensional picture. Now that you have a length 2, well, a 3-term resolution. So now again, you're going to build up these. There's 4 summands. You'll build up 4 sets. And then the first one will be 0-dimensional. Then you'll have some graphs, and then when you build the last one, that's going to involve a cone point, and then you're coning from that point to a bunch of graphs. So you wind up with a bunch of 2 simplices connected to that. So that's all the kind of our story. So yeah, it's spectral, we circle back to the other half of the first slide, closing remark. So I said at the beginning, kind of, what is a generalized dimer model? That is a question that people have thought about before. From a different point of view, what was this other point of view? So I alluded to this observation of thing, a coamoebae, that says, well, if you just start with a curve of C star squared, and you look at a coamoeba up the curve. So here's a picture they computed what one of these coamoeba looks like. And it looks like a kind of a bunch of polygonal regions that are kind of taped together at their corners like that. And that picture is dual to some bipartite graph now. And their observation was that if you take that bipartite graph and you look at it, the dual quiver, for just the Poincare dual graph, if your original graph is bipartite, the dual graph gets an orientation by saying, like in dual quiver, an edge is oriented so that it passes a white vertex on its right. So you get a quiver out of this graph picture, and the arrows in that quiver will correspond to intersections among the vanishing cycles of the spectral curve. So this bipartite graph is a kind of pictorial way of encoding the vanishing cycles of the curve. And they were interested, there were various reasons they were interested in them, but geometrically, the key thing is that so as we said, a curve has a Newton polygon. Associated to a Newton polygon is an affine toric threefold. So in general, affine toric varieties are labeled by rational cones. So I can take the rational cone over a lattice polygon, say placed at like height 1 in Z3. Take the cone over that gives me a toric threefold. And the mirror of that toric threefold is something that looks like. You take this spectral curve. Okay, E of x, y for its equation. And now I can look at dxy equals uv. Where this is now in c star squared across c2. So I've stabilized the spectral curve into a spectral threefold. So now I have an equation in 4 variables. And the claim is this is the mirror threefold to the toric threefold associated with the cone of the spectral. Right, so that's mirror symmetry for toric threefolds. And the vanishing cycles of the spectral curve. So vanishing cycles of the curve give rise to Lagrangian spheres in this threefold, right? So for that reason, if you want to understand toric mirror symmetry, you want to understand vanishing cycles of curves, and the graphs give you a convenient way of encoding that. And that is the perspective that these people were thinking about. So they asked, well, what can you say about toric n folds for more general n? There should be a similar story, but now you want to study vanishing cycles for higher dimensional hypersurfaces. And to some extent, this is one of these things that was kind of worked out in the physics literature, and it would be really great for some mathematicians to kind of clarify what all they had done. But anyway, there's some kind of reasonably fleshed out story where for a general hypersurface, you can find some kind of codimension 1 polyhedral complex, which plays the same role. So the hypersurface itself will deformation retract onto this polygonal polyhedral complex, and a suitable version of the dual quiver of this complex will record the vanishing cycles of the hypersurface. So that is some other so this is some generalization people had worked out. But as I said, the starting point was that there's something missing here, because the big picture is that different parts of the dimer model in dimension 2, some parts are about the spectral curve kind of as a hypersurface. So the stuff about vanishing cycles fits in that bucket. But some things are about the curve as a Lagrangian. So a curve in c star squared has this feature that, of course, it's an algebraic object, but it's a holomorphic Lagrangian. So after I can hyperplanar rotate, I just have an ordinary Lagrangian. And that's some version of this combinatorial construction of LVM up from earlier. So anyway, so if you wanted, and the spectral transform was really about the curve as a Lagrangian in this part. So anyway, the dimer models in 2-dimension, there's really 2 general theories that are kind of intersecting. This is the kind of big picture. And they intersect because curves in c star squared are the intersection of hypersurface geometry and Lagrangian. All right, I think that's a good place to stop.